Okay, done. Right. Very good evening to all of you. Before we start our lectures, so please take notes for these important dates over here. Okay. Yeah. I think first of all, so I think probably you guys already aware. So I have already posted the assignment 1 question to the Spectrum. So you can actually download the question from the Spectrum now, right? Okay, so let's come back to here. So assignment 1, so the duration will be 1 week. So today, just posted, and the submission will be 3rd of December, so week 7. And next assignment 2, so I'll be given, the question will be given on 31st of December, and the deadline is 14, not December, I think, sorry, this is wrong. January 14th of January, yeah, 2022. So the duration for assignment 2 is 2 weeks. Yeah. And finally, so it depends on the exam here. Yes. So let's look at our exam first. So the exam will be 3 hours, 3 to 6. Okay, so will be on 15th of February. Okay, that is actually the 2nd week in the exam week, week 16, Tuesday of it. Yeah. So I suppose you all can make it. So if you really cannot make it for some very urgent or important things, so please let me know as soon as possible so that I can discuss, see whether I can reschedule the date or not, right? Okay, next will be week 14. So this one test, I will put it on the week 14. Yeah, so 6 to 7. So I hope after we have finished all the lectures, though we have some time, then we run our test rather than I put it in the middle of it here. Okay, so this is the date for important date for our course here. Right. So especially for the exam. So if you're already having issue with this time, so please let me know by latest this week Sunday. Okay, so that I can see whether we can do a reschedule on it. Okay. Final exam date. Okay, so please let me know. By this Sunday. Yeah, so that I try to make a arrangement for that. Okay. Of course, please give me a good reason for it. Okay, if you want me to reschedule it. All right, so that's the important date for it. Okay. Sorry, I just can't remember what is the scope for this test. I will let you know the scope. Okay, so most likely will be chapter 1 and chapter 2. So the scope. So I will let you know later. Okay. Okay, so that's the important date for our course here. Okay. Now we shall proceed to our lecture, chapter 3. Okay, so this is our lecture note. So I will just discuss all these things. Okay, first of all, I do a summary over here. I just write down all the important formula concept over here. Okay, so after that, for the example, I will refer back to our lecture notes here. Okay, first of all, let's look at these two definitions here. Okay, so let's begin with this. Supposing we have events A1, A2, A3, AN actually it can be extended up to infinity. So we set it okay, we said all these events are mutually independent whenever we have this, okay, PA1, A2, AN equals this. And we said that they are pairwise independent, okay, mutually. So we have this. If we say they are pairwise independent, so that means we just consider the independence on a pair, any pair of them. So that is P of AI and AJ is equal to P AI multiplying AJ whenever AI and AJ are two different events. Okay, so you can see when we taking n equals to 2, so these two are identical. These two concepts are identical. That is, we just simply call they are independent. That is PA and B equals to PA times PB. So however, when we come to n more than 2 events, so these two are not identical. So we here. Yeah. So just to let you know this, so in general, so this is actually our remark. Maybe I just put a okay, 3.1.1. Pairwise independence does not imply mutually independence. Okay, so that means we have a set of events. They are pairwise independent, but they are not mutually independent. So we will look at an example later. Okay, to look at this thing. Okay, so we will look at an example later. So 3.1.4 for it. Okay. Okay, so this is okay. First, we look at the first examples here. Okay, so this is in example 3.1.2. So n unbiased dice is tossed twice. Okay. Okay, so it tosses twice, 2 times. Okay, so A be the event, sum of the number that appear it's equals to 6. So A, sum of the number appeared is 6. And next we look at the events. B is the event. The number on the first toss is 2. And C be the event that the sum of the numbers that appeared it's 7. So then we have to check event A and B are not in the let's check this. So let's look at our case here. First of all, if we have a dice, it tosses twice. So that means we're going to have 2 of them, right? So omega 2 times. So that means will be omega 1, omega 2. Okay. So whereby omega 1, omega 2 will be 1, 2, 3 up to 6. Okay, so you can see the cardinality, the number of elements inside here will be 36. Okay, so I think it's quite straightforward. Okay, first of all, let's look at A. A would be the event, sum of sum of the number that appear to be 6. So that means the sum of these two, we get 6. So that means event A will be, so either how we get 6, 1, so 2, 4, 3, 3, and 4, 2, and 5, 1. I think that's it. So others will not give us value 6, right? Okay, so this is our A. And for B, so they said where's B? The number of the first dose is 2. So that means, so F, so we 2, 1, 2, 2, so 2, 3, 2, 4, 2, 5, and 2, 6. And C will be the sum of the two numbers, we get 7, so it will be similar to this. So that will be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. I think that's it, right? Okay, I think from here, again, we always assume this will be follow uniform distributions. Okay, so that means or this is unbiased, right? So unbiased, so that means it's we always follow these uniform distributions. So that's why from here, then we can easily see 1, 2, 3, 4, 5. Total is 36. So that's why you can see the probability of A will be 5 over 36. So the probability of B will be 6 over 36. The probability of C will be 7 over 36. So we look at the intersection of A and B here. So A and B, which one are intersections? So I think so 2, 4. Anything else? Okay, I think that's it, right? 2, 4. Huh? So that's one. So 2, 4 here. So then from here we can see P, A, and B will be 1 over 36. So I think which is clear if we compare to here, for sure that is not equals to I think obviously not equals to 5 over 36 times 6 over 36. So from here, then we can easily see that. So A and B are not independent. So yeah, so it's a easy arguments here. And also, why event B and C are independent? So we have to check this again. So what is the event B and C? So overlapping here. So which one identical? Okay, so 2, 5. So we got it. I think that's it, right? Yes, 2, 5. Huh? Okay. Why is that so? The sum of the number that appear is 7. How do we get the same? Level 6. I think forget about it. I think I made a mistake over here. I think cut this part. Okay, B, C are not independent. Okay, what I'm trying to say here actually.
The probability of C is 6/36, no?
6/36, is it? 1, 2, 3, 4, 5. Oh, okay, yes, correct, then correct. Yeah, thank you. How stupid I. Okay, yeah, right. Then this is correct. So yeah, 1, 2, 3, 4, 5, 6. Yeah, it's 6. Then no problem, no issue here. Yeah. So 36/36. Yeah, correct. Thanks. So then we can see, yeah, we get the same thing. So B and C is equals to the event with only one outcome, 2, 5. So we can see, that's why we can see P of B and C is equal to 1/36. That is equal to 1/6 multiplying 1/6. That is equal to PB and PC. So yeah, so this is a simple calculations here. So then we can make a conclusion. BC are independent. Okay. So this is a simple example how we can calculate this. Okay. Am I right? Okay, so we look at the next examples. So this one we have to go try to illustrate this idea. So pairwise independent does not imply the mutually independent. Okay, so okay, so this one does not imply this one. So just look at the examples here. Okay, so 4 identical balls in and on are marked as follow. On one ball, we write A, B, C. So then, while on each of the remaining 3 balls, we write A, B, C respectively. So that means we have 4 of them. So event A is of A, B, C, we come together. And then this one A, B, C. So we have all 4 of them. Yeah. So draw a ball at random. So EA denotes the event symbol A appear on the chosen ball. So then we will get all this and so on. So you can see we have a 1, 2, 3, 4, right? I think we choose one. I think it's clear, right? So you can see each of the alphabet appeared 2 times. So we have 2B here, and we have a 2A and 2C here. So that's why I think it is very obvious. We can see P of EA will be half. All this will be half. Okay, so and also PEA and EB. All this must be the same. Must be 1/4. So why? Because of that's the only possibility that appear to be an EA, EB. So this is the one, right? So I think from here, then we can easily see that all these are 1/4. Then you can see event A, B, C are pairwise independent, but not mutually independent. So the reason is this is half, right? You're multiplying 3 of them. So we also have a PA and PB and EC will be 1/4. So I think from here it's straightforward. So this is 1/4. Then we can see P of EA multiplying P of EB multiplied P of EC will be 2 multiplied half multiplied, so it's 1/8. So these two not identical. Okay, so it's not identical, then we can have a conclusion. So EA, EB, EC are not independent. We should check. She said this is not mutually independent. Okay, so this is a simple example whereby pairwise independence does not imply mutually independent. So I think this is a straightforward thing. So let's proceed to our next topics here.
Is it true the other way around?
Yes.
Also?
Yes.
Okay.
Yes, the other way around is true. No. What do you mean by the other way around?
If it's mutually independent, is it also pairwise independent?
Yes, mutually always pairwise.
I see. Okay.
Mutually always pairwise. Okay. What I mean, the other direction is always true. Okay. Okay. Next, we proceed to this important result here. Okay. The so-called the Borel-Cantelli lemma. Okay. So we have the two events here. Right. So two of them. First one, no additional assumption. So we only need this. When the summating of the probability of all the En is not infinity, then P of limit supreme of En will be equals to 0. Okay. And the second one, we need one additional assumption for it. If they are independent. If they are independent. Okay. So then if this is infinity, we have this. Right. Okay, so maybe let's give you this indication here. Okay, first of all, this is always true. If this is not infinity, you imply this. Before we look at the proof, just look at this. So first of all, this is always true. If this is not infinity, okay, less than, so this always imply P of ANIO limit supremum of AN is equals to 0. Okay, and the next one, if we add in one additional assumption, all the AN are independent, then we have this. So if AI are all independent, so independence here will always means the mutually independent. Okay, so then we have this. When this is infinity, then we have P limit of supremum of AN is equals to 1. Right, so we got these two. Maybe I put a label here. So this is A, this is B. Okay, this is A, this is B. And before we proceed, so I think you guys still remember this, right? We have actually discussed this in our first lecture. So limit supremum of AN is actually stand for infinity often. Okay, infinity often. So this one just simply means that the outcome will appear infinity many times. Okay, so it will appear infinity many times. Okay, but we don't know when it will appear. For sure, we know it will happens and happens and happens again. Okay, but we don't know which day. It's sort of like how is it? It's sort of like we are uncertain which day is going to be rain, but for sure, someday it will be raining. Okay, it will be raining in some day, but we don't know which day. It could be tomorrow. If tomorrow is not raining, so maybe the day after tomorrow will be raining. Okay, if the day after tomorrow is not raining, so maybe after a week it will be raining. Okay, and some other day it will keep on. Okay, so this is the meaning for this limit suprema of an. Okay, so this is the probability interpretation for this symbol. Okay, next we look at this interesting implication here. So if without any additional constraint on our sequence of event an, so this is that is a statement A. This is always true. However, if we always consider independence events, so what can we happen? So this is the case. So we assume this. Okay, maybe I'm not assume. We say when these AI are all independent. So when we say independence, that means mutually independent. Okay, are independent. So we have two different cases. Case number one. What I want to tell you already. Okay, yeah, okay. So this is the case here. Okay, case number one. So let's say we have this, the probability of limits. Okay, so maybe this is the one. Let's say we have this. What's the argument? So the probability of limit supremum, case number one is not zero. What's happened? Okay, so in this case, right? So you can actually just cover, forget about this. We don't really need this independence or not independent. Okay, at the moment we don't need it. So you just look at here. Supposing probability of limit supremum an is not zero. So what happens? So we can just look at here. When the summation of PAN is not infinity, we get the probability of lim sub an 0. So when this is not 0, then we must get this is equals to infinity. Okay, so then from here we can see, then we must have the summation of P of an. Okay, this one I don't have to. So must be equals to positive infinity, right? Now you can see actually this conclusion do not need this assumption. So even with or without this independence of an, so we can always draw this conclusion based on our observation here. Okay, so this is always true. Yeah, that's it. Okay, next, if this is positive infinity, on top of that we have assumed that, or we know AI are independent, then we make use of B. Okay, independence and this. So if we have this, then this must be equal to 1. So now using this and this, so what can we have? So that means we can always draw this conclusion, that is P of limit supremum of an must be equals to 1. Right? Okay, so I think agree. Yeah? So just a simple logical derivation. This is what we can have, right? So I better put 2. Okay, so now if we look at this probability of limit supremum an, so we can always have 2 different cases only, right? So we don't have any extra cases. So it will be either the probability of lim sub an is equal to 0, or this is not 0. I think it's clear. So if you have a non-negative numbers, so it will be either 0 or it will be either non-zero. So 2 different cases, right? But however, for the second case, when this is non-zero, then we can always draw a conclusion. It must be equals to 1. So from this, we can draw a very interesting picture here. That is, we can make do this conclusion. Okay, from this observation, we can have this very interesting conclusion. So that is when A1, A2, and so on are all independent. Okay, then we can have either limit supremum of an is 0 or limit supremum of an is equals to 1. It cannot be others value. It will be either 0 or it will be either 1. Okay, it cannot be half. Right, so that means we have a very nice result here. Okay, so this is always true whenever we consider a sequence of independent events. Okay, A1, A2 are all independent. Then we can have either limit supremum of an is 0 or limit supremum of an is equals to 1. So that means it will be either true or it will be either false. Okay, so that means the conclusion will be very certain, either yes or no. It cannot be uncertain. So that is the conclusion that we can draw from our observation here. So based on these 2 results, A and B, which are our Borel-Cantley lemma. Okay, these 2 are so-called the Borel-Cantley lemma. So that is another way to describe our Borel-Cantley lemma. That is this: when A1, A2, and so on are independent, then either limit supremum an is 0 or limit supremum an is equals to 1. So that's why.
Sorry, doctor.
Yes.
I want to ask, what is the difference between the probability of limit supremum and just the limit supremum?
Oh yeah, thank you. I should have put in the probability here. Yes, right. Thank you.
Okay.
The probability, yeah. Okay, so yeah, the probability is either 0 or either 1. So that's why very often we call this as what do you call it? Law of 0. Okay, doesn't matter. I think the idea is this is so-called law of 0, 1. It's supposed to be Borel laws of 0, 1. Okay, so which means the probability will be either 0 or either 1. Okay, whenever we have a sequence of independent, what do you call it? Independent events. Okay, so this can be obtained from these two lemmas here. Okay, so this is it. Okay, so this is one very interesting probability interpretation that we can draw from these two theorems here. Okay, so now we proceed to the technical part for it. Okay, so let's look at the first proof for the first result. Okay, so this is our first result. Maybe I can just put it over here. Okay, so this is our the statement for our first program counter lemma. So actually, it's a very straightforward. We do not need any hypothesis. We only need one. So provided the summation of all the probability an less than 0. So this is equals to 0. Okay. So let's look at the proof for this. Okay. Before the proof for it, so we need to recall some technical results, okay, before we look at the proof. Okay, just to recall some of these things. Okay, first of all, limit supremum of AK. So it just simply means in a way, this is actually equals to infimum, supremum for it. Yeah, infimum always stands for intersection. Supremum, in a way, you can say which is a union, right? So this is actually equals to the intersection of n from 1 to infinity of our Bn here. And what is our Bn? And our Bn is defined as we submitting a union or the AK, k running from 1 to infinity. Okay, so this is the thing. Okay, so maybe I'll go and put it over here. That will be better. So if you want to write, so that will be an or an plus 1 or an plus 2 and so on. So first two things. First of all, limit supremum is equals to Bn. Bn is this. And next, we also have another properties. That is, this Bn is an increasing event, meaning that B1 always smaller than, not increasing. Bn is decreasing. Bm is a decreasing sequence of events, so which means B1 is B1 is the largest one, and B2 is smaller than B1, which is contained inside B1, and B3 will be contained inside B2, and B4 will be contained inside B5 and so on. Okay, so this is the definitions or the observation that we can get it from the definition of Bn here. Okay, finally, we have an important formula here. When Bn is a decreasing sequence, then P of intersection of them, so will be equals to limit something. Okay, whenever this is a decreasing sequence, so we always have this. So one by one, okay. This is not important. This is not important. The most important is this part and this part. Got it? So limit supreme of AK is equals to the intersection of our Bn. What is a Bn? Bn is equals to the union of AK, K running from n to infinity here. Okay? And this is what we can deduce from here. So directly we can get it. So just look at these properties. Okay, so you just look at the first one and the last one here. Okay, now we can look at the proof for this Cantley lemma here. If this is not infinity, then this is B equals to 0. So let's look at the proof for it. Okay. Right, so we assume this is not 0. Okay, we only need assumption that is if we summating all this probability of k running from 1 to infinity, which is not infinity. Okay? So on the show, this is equals to 0. So we just look at here, P of limit supremum of an. Okay, so from our previous construction here, this is the intersection of all the Bn, right? So that's why we can always write this one as P of intersection of Bn, and from 1 to infinity. Okay, next, we know the Bn is decreasing sequence of event. So when Bn is decreasing, we can have this formula. So this formula implies that we can have this is a limit n running to infinity, P of Bn. Okay, so before that, what's the meaning of our Bn here? So Bn is equals to the union of all the AK, K running from n to infinity. Okay. So we can put it this inside. So this is a limit n to infinity of P of. Yeah, this is the case here. Okay, again, remember our Boy's formula. So I think in tutorial 1, so we have this, right? P of A or B always less or equal to PA plus PB. Okay, so if you have a union, so that means this will be less than the sum of them. So from this, then this can be always less. This is always less or equals to, we have a summation K running from n to infinity of P of AK. Okay, so now we want to, not yet, so maybe we write one more step first. So we can actually write this into this way. Okay, so so this one will be we summing n onwards. Okay, so n plus 1 and so on up to infinity. So that's why we just add in, we starting on beginning and then we subtract this. So we just subtracting the first term up to the n minus 1 terms. So this is the case here. Okay. Right, so there's no n here. So that means this is a constant, we can take it out. So this one will actually becomes, so less than, without n here, so that's why we can take it out without using the limit of it. So minus. So when you put it inside, so this is the case here. So when you substitute n is infinity inside, so this is actually end up with things like that. So this is less or equals to k is from 1 to infinity p a k minus this. Okay, so this is this one minus this. Okay, next, this is why we want these things. So why we want this assumption here. This is not, maybe this one. This is not infinity. So why we want this when this is not infinity. So here, this is not infinity. This is not infinity. So that means a number minus a number. So that will be always equals to 0. So that's why we want not infinity. Why? The reason is infinity minus infinity, we don't know what is it. Okay, infinity minus infinity is not 0, so we don't know what is it. We just don't know. Okay, so if you have, so still recall what you have learned in calculus. It can be different answer, depends on the pattern of the thing. Infinity minus infinity could be 0, could be infinity, or something else, right? So that's why when this number is not infinity, yes, no problem. A number minus the number itself must be 0. Okay, so this is less or equal to 0. So that means this part is less or equal to 0. So that's why we can have which is always equals to 0 here. So this is the end, how we can prove the first one. So this is steps over here.
The conclusion that the probability of limit superior an equals to 0 is equals to 0 is because it's a probability, right?
Yes,
because it's less than because the conclusion is less than 0, but then we say the limit supremum is equal to 0 is because of probability of limit supremum is a probability. So then is that why? Is that the conclusion?
Yes, because of probability cannot take negative value, right?
Okay.
Okay. So this is less or equal to 0. Then we can probability can never be less or equal cannot be a negative number. So when a which is less or equal to 0, it must be 0. Okay. So that's why we can say hence it must be equal to 0. Oh, okay, I always forgot this one. So this is one good examples, okay, of or good exercises to demonstrate to you guys how we going to use all those formula or result to draw certain conclusions. Okay, so you can see this is what we can use. Okay, we are actually using, I can't remember this what theorem is this. This is should be a theorem in chapter 1. Okay, you guys go and look at the I don't know what theorem is that. So this is a theorem in chapter 1. Okay, I don't know what's the numbering. You guys go and check it out. So we make use of this and the definition of limit supremum, right? And so that's why we need this, okay, because of this part here. Okay, just to remind you again, mathematically, we don't know what is it, infinity minus infinity.
Dr. Lu, can you please re-explain the step in the red brackets from the step before that to the step in the red brackets?
This part.
Yes.
Okay. Actually, it's not difficult. The problem is where should I? Okay, I'm going to put it down here, down there. Okay. So this thing, why this thing equals to this, right? So it's not difficult. We can actually forget about the limit. Just look at it. So this is PAN plus PAN plus 1. Right? So N plus okay. Oh, where is it? Why the rule? Forget it. So I just put it here. So this one equals to this. No problem. You guys can agree, right? So let's say you add PA1 plus PA2 plus PA3 up to PAN minus 1. So what would you get for this part? So this is equals to this, right? You are summating all the PAKK running from 1 to 1, 2, 3, 4, 5 up to N minus 1. We continue N plus 1 and so on, right? So this is what, okay, and then since we have an additional, we have to do a subtraction. So we minus, make it balance, right? Forget about, just look at here. These two are balance, right? Minus this. So this is what we can have. Okay, now you just group this part. And here. So then you can see, so that's why this is how we can get, if we're grouping these first two lines, we can have K running from 1 to infinity, P of AK. And what is this? So this is actually your minus subtracting P of AK, K running from 1, 2, up to N minus 1. So okay, so this is how we can do this. It's not difficult, it's just a matter of symbol.
All right, thank you.
Okay, just like that. Okay, so I think once you are aware of this kind of derivations, okay, you can decompose it into two parts here. Okay, the remaining will be the same. Okay. Okay, so this is how we can get the first conclusions. Where is it? So that is our first counterly lemma. When the summating of PAN is not infinity, P of limit supremum AN will be equals to 0. Okay, so if you want to go to the other way around, so we have to put in additional assumptions here. We assume all the events are independent. Then we can draw the converse for it. Okay, so this is okay. Before that, we need to use this result without proof. So I think you guys go and check it out. So you might need to check this. Okay, you might need to verify this first. Okay, that is when A, B independent. So then all these also independent. I think maybe I can A and B complement are independent. How should I say that? So maybe you should say then all of them are actually independent. Maybe I just put this one. Then the complement of A and complement of B also independent. Okay, so you might need to verify this result first. So this is one result. When A, B are independent, then the complement of A and complement of B are independent. So in fact, this is more general. We can have more result for it. So you can see also we have to have this. When A, B are independent, then A together with complement of B also independent. In tutorial 3, if I'm not mistaken. So, however, in our proof here, we only need this A, B independence, A complement, B complement independent. Okay, so this is one result that we going to use here. Okay, so this is what we so-called the second Borel-Cantelli lemma. This is actually the converse for the first version, but we need an additional assumptions when this is independent, then we can have this. Right, so what we can have, we assume this AI are independent. And also we assume this is infinity. Okay, these two are, this is independent, this is only. Okay, so this is independent according to our, but I didn't prove this for you, so you guys go and verify on yourself. This is independent, so their complement also independent. So, and I just put it over here. This is independent, so this will imply that we also have the complement of them are independent. Okay, I'm not going to prove it, so you guys go and verify on yourself. So you may refer to this tutorial 3. So similar way you can prove it. Yeah, you also have this. Okay. Okay, next we do this. We want to show this is equals to 1. And we just begin with this P of limit increment of AK. Okay, so we're looking at compare of AK instead of AK. So to do this, we actually need to recall similar ideas for it. Okay, which is actually something like this. Okay, something like our previous results over here, but okay, but we are using the other version for these things. Okay. So maybe I'll put it over here. So recall, if you have limit infimum of some things here. So since I'm using compare AK, maybe I use another symbol. So instead of AK, let's say I put this one to be E. Okay. So this is actually equals to limits of Cn, n approaches to infinity. So the idea is exactly the same as the previous one. Limit infimum is sort of like a supremum infimum. So this is sort of like the union and intersections of our EK. Okay. So what is our Cn here? So the Cn is actually equals to the intersection of all the EK k running from n to infinity. So that is just en intersect en plus 1 and so on. And also with a similar result, then we can have this, the probability of union of Cn is equals to limit of n to infinity of p of Cn. So this is again the same result that we have used in the previous proof. It just but the other version for this. Okay, now we can come back to here. Now we can replace our ek to be akc. So then we can see this is just equals to the probability of limit n to infinity for Cn. Okay, what is our Cn? Where Cn is just equals to the intersection of all the complement of ak, k running from n to infinity. So then we applying this formula, then we can see this is equals to limit n to infinity of p of Cn. Okay, now we substituting this inside here. So this will be equals to limit n to infinity p of ANC plus an plus 1 complement and an plus 2 complement and so on. Okay, all right, so and because of this, all these are independent. Okay, by using the definition, independence here always mean mutually independent. So this is independent. Then by the definition of independent, so this can be written as P of ANC, P of an plus 1C, P of an plus 2C, and so on. So we just keep on multiplying each of the numbers here. Okay, so we do not need that anymore. So, but now we look at here. We have another property. So this one can be written as this. So this one can be written as 1 multiplied PAN for the first one. First term will be this. So the second term is the probability of the complements of an plus 1. So again, we can put it as 1 minus p of an plus 1. Likewise, this one, that will be equals to 1 minus p of an plus 2, and so on. We keep on multiplying all these things. Okay, next, there is one formula in calculus which we didn't put it in our lecture here, so we just use it without verifying it. Okay, that is, we have this formula. So this is something that you have learned, you should have seen in calculus. For any positive number, 1 minus x will be less or equal to e of minus x. For any non-negative number x. Okay. All right, so we are not going to verify this, okay, over here. So you can refer back to your calculus textbook. So we should have this formula again. 1 minus x is always less equal to e minus x. Okay. How to do it actually is, again, this is a calculus thing. It's not difficult. That is just means that if you put fx is 1 minus x minus e minus x, right? So then the maximum value of f will be equal to 0, something like that. Yeah. So that's why this is always less or equal to 0. Of course, when you're talking about when x is non-negative. Okay. All right. That's not what we want to do. So we just applying this. So we applying this into our formula here. So then our expressions will be more or less like less or equals to limit n to infinity. So this one will be e of minus p of an multiplying e of minus p of an plus 1 and so on. Okay, and then by using the properties of the exponential function, so this can be written as limit n to infinity e of minus p a n. Okay, maybe we put a summation here, a bracket. So this one, it's supposed to be a minus minus minus, so p plus 1. Okay, so for these terms, this term is actually equals to minus. So since you begin with n, the n plus 1 up to n plus 2 and so on. So this term can be written as minus of the summation of p a k. First term is n, second term is n plus 1. So that's why k will be from n up to infinity. Okay, just following the running script here. Okay, so now if we let n to infinity, okay, so that means it doesn't matter where this is n. Okay, then we come back to this. So our assumption, so this is equals to infinity. Okay. So this can be written as this. So that means by our assumption, so this is always equals to negative of infinity. So if this is a negative infinity, so this is actually independence of the value of n here. It doesn't really matter. So this is e power of negative infinity. So that's why this is always less or equal to limit n to infinity. So okay, maybe in a way you can say I don't want to put this. So this one, in a way you can say this is a limit n to infinity e power of negative infinity here. So that equals to 0. Okay, e power of negative, sort of like things like that. So therefore this is a 0 here. So then this is 0. Okay, what we want to do, actually you can come back to this. So we have shown that this p limit in front of a k complement is equals to 0. So this is what we have. So this is equal to 0. Okay, next thing that we can directly see. So hence, okay, maybe we just verify this first. So you can actually verify this, the complement of limit supremum of AK. So like I say, limit supremum is actually equals to infimum supremum of AK. Okay, so infimum stand for intersections, infimum intersection, supremum in union. So this can be written as intersection union of AK. So of course, if you want to fill it in, so that will be this is index k, right? K running from n to infinity. So n, so n from 1 to infinity. Okay. So complement, then we can make use of our De Morgan's law here. So this will become union intersection AC. Okay, how to use it? So this is actually by using De Morgan's law. So again, you can always assume, put it this way, infimum represent intersection, supremum represented union. So union, so that means we can replace this with supremum, infimum of A, K, C. So, and again, this is just the definition of this. So this is what I'm trying to tell you is we have this. Okay, what I'm trying to tell you will be this one. Okay, so this is a very interesting, important formula. So you may just remember it. So how we deduce will be like that. So that is the no, the complement should be outside. So the complement for limits lim sub AK will be lim in AKC. Okay. Okay, now we get the probability for this part is equals to 0. So then we can see the 1 minus the probability of limit infimum of AKC. So that is equals to 1 minus 0 equals to 1. So that's how we get it. Oh. Okay, so this is how we get the first the result here. Okay. Okay, so conclusions again. So this is the result. Borel counter lemma. So when the summation of PAN is not infinity, P of lim sub AN is 0. So the second Borel counter lemma, if this is independent, the summation of PAN is infinity. So P lim sub AN will be equals to 1. Okay. So this is the proof for it. So this is another properties that we are using here. Okay. Okay, so we look at the application for this lemma. So we can use it to deduce some interesting result here. So let's look at the examples. Oh, okay. So this is actually the proof for it. Yeah, so which I have already discussed just now. Okay, let's go to example 3.1.6. Okay, let's look at our example here. So x1, x2, x3 is a sequence, be a sequence of independent Spannerian trial. Okay, with probability of success equals to pk on k trial. So find the probability of, okay, so this is what we have, the probability of n events of success for each of the following cases. So pk is 1 over k squared, or pk is 1 over k. So this is what we want to calculate. Want to know the probability of infinite number of successes. So okay. So that means then you can see what's the implication for you. Let me see. In this case, so xk is equals to 1. So this one will be the event whereby the k trial is success. Okay. Okay. Likewise, when we put 0, that means this will be fail. Okay. Okay, now we look at this event. Infinity numbers of success. So what is how are you going to describe this event? Okay. So what is how are you going to describe this event of infinity number of success? So like I say, in the early beginning, where is it just now I have said that infinite number of success means this outcome will occur infinite many times. So therefore, this is actually can be represented by this event. That is, we look at okay, maybe we can say this. We write this one as AK. Okay, AK will be the event that the K trial is success. So that is X is good. So the events of infinite number of success, so that is can be represented as AK. So it occur infinity many times. So in other words, how are you going to describe these events mathematically? So that is just equals to limit supremum of AK. But in here, we are using the symbol to represent AK. So now this is our case here. So that's why this is the limit supremum of AK is equals to 1. So that means now this is what we want to know. Okay, now we know what we want to compute. So we want to compute the probability of this. Okay, according to our questions, so we assume this is a fair trial. So fair trial means each trial is independent. Okay, the previous result won't affect the future result. Okay, so then we can use our second Cantley lemma. Okay, where is it? Here. When the event is independent, and if this is infinity, so this is equals to 1. Okay, of course, when we don't know whether this is independent, so when this is less than infinity, this is equals to 0. We can use this result to solve this issue. So then the question is A. We have 2 different cases when pk is 1 over k squared. Oh, okay. Oh, then we assume this is not a fair game. So in this case, so we can see this is not a fair game. Yeah? So because if this is a fair game, then must be half here. Okay? If this is not a fair game, so pk is 1 over k squared. Then we can see this. So we just look at, we do the summations of p of ak. So that is just summating of 1 over k squared. All right, so this thing is not equals to infinity. This is by a result in calculus. So you guys should have seen this kind of result in calculus courses before. So by topics in calculus series, okay, topic series topic series in calculus. So this is not infinity. Okay, when this is not okay, when this is not infinity, so we don't have to worry about whether it's independence. Okay. When this is not infinity, the probability is always 0. So that's why we can straight away draw the conclusions. So the probability limit supremum of ak will be equals to 0. Yeah. So that's why when this is not a fair game, so which means after a while, there's no more success. Yeah. So this one 0 means after a while, no more success. Okay, this is one reason because it's not a fair game, 1 over k squared. Huh? So that means we don't know how many of them. Maybe only we can have 100 times of success. After that, we always fail. We cannot get success case. Okay. Okay. So the next one, if pk is 1 over k. So actually, what we need to do is we do the similar calculations. So what we just need to compute the summatings of p of ak. So this is we substitute inside 1 over k. Okay. So again, this is actually equals to infinity. Okay. So this is by a result in calculus. Okay. You may refer back to what you have learned in calculus. So, but I don't care about what method. So what I consider is this is equals to infinity. On top of that, we have assumed, okay, not here. Okay, so this is infinity. On top of that, so we have assumed our events are all independent. Okay, so then we just refer to this second Cantley lemma. For independence events, when the summation of the probability is infinity, so the p of this is always equals to 1. So that's why then we can see this. And the probability of limit supremum of an will be equals to 1. So that's why we can always have a success case, no matter how. So let's say we look at the extra. Let's just see, this is extra. So suppose PK is half. Okay, just imagine we have tossing a coin. A fair coin. So P of head must be half, and P of tail must be equals to half. So let's say PK is half, and this is a fair coin. Then we can see if we do the summations of P of AK, so we have a summating of 1/2. So again, this is a geometric series. We can get this is 1 minus half. So that is half. This is not equals to infinity. Oh, no. Sorry, I made a mistake here. Cannot be infinity. Oh, sorry. What's the meaning of it? So that means we are keep on adding half for infinity many times. So I think it's clearly we can get this is infinity. Yeah, we must have infinity. All right, so this is infinity. So when this is infinity, so then we can see P lim slope of AN will be equals to 1. So that means in this case, then we can draw a conclusion. What does it mean? So that means for a fair coin, okay, for a fair coin, so we keep on tossing a coin, so we can get infinity many times of head. Yeah, so I can see this is actually follow our intuitions, right? Our human intuition. If you keep on tossing a coin, so it is almost impossible you will always get a tail unless you are cheating, right? So that's why for a fair coin, we can always get infinitely many times of head. How many of them? When will it occur? We are not sure, but for sure, after a while, we can get a head. Okay, and after a while, we can get the second head, and so on. So this is something that we convince the thinking, the logical flow that happens in our mind, right? Okay, so 7:30, yeah, good. I think it's a good time for us to stop here. Well, we stop at these examples, okay? Then we continue our second section on 8 o'clock, so section 3.2, okay? So, okay, see you guys later.